we got a torsion pendulum problem. So let's take a look. It says a uniform solid metal disc of mass 6.5 kilograms and a diameter of 24 centimeters hangs in a horizontal plane, supported at its center by a vertical wire. You find that it requires a horizontal force of 4.23 newtons tangent to the rim of the disc to turn it 3.34 degrees, thus twisting the wire. You now remove the force and release the disc from rest. What is the torsion constant in the metal wire? What are the frequency and period of the torsional oscillations of the disc? And then write an equation for theta. Okay, we can do all those. So since this is simple harmonic motion, we have some similarities with other simple harmonic motion problems we did. I would really like to make some connections between doing torsion pendulums and mass spring problems. There's a lot of similarities to be had there. One of them is, what is the torque produced by a torsion pendulum? So the torque is equal to some constant times theta. So we got the torque from a torsion pendulum is equal to beta theta. That's similar, even though it might not look like it, to force is equal to K times X for a spring. So think about it in that respect, and it makes it a little easier to kind of come up with some of these values. Okay, so let's fill out some information here. So they are looking for us to find beta. Okay, so the torque you apply is always going to be your force perpendicular times how far from the axis of rotation you applied it. And if I'm solving for beta, I just need to divide theta over. So let's see what numbers we got here. So we had 4.23 newtons, and they gave us a diameter of 24 centimeters. So we got to half that, so 0.12. Divided by, they gave it to us in degrees, 3.34, and I got to get rid of degrees, so 180, and go to radians, pi. Put that into my calculator, and we get, whoops, didn't quite do that, 8.7-ish, we'll call it. 8.7, and the correct units here, we're going to have Newton meters per radian. As that value, okay? All right, part B then says, what are the frequency and the angular frequency? So we're gonna start with Newton's second law to go ahead and solve this one. So starting here, there is going to be this torque from the torsion pendulum, from that wire, and it's always going to be opposite the way I rotate it. So when I think about this torque here, it's going to be negative beta theta. It's going to be the opposite of the direction that it's been displaced, equals I alpha. And so now we just need to fill in some information. So they did tell us it was a disk. So they did tell us the I value. And they're asking us to find omega. All right, so we'll remember that for simple harmonic motion, it's always going to be something along the lines of the acceleration is equal to negative omega squared x. And in the rotational sense, this looks like alpha is equal to negative omega squared. And the key point here to note about omega, that is the angular frequency, not the angular velocity in this case, times theta. So I just need to get this equation into that format to figure out what that omega value is. So I divide the I over, and so I see I have negative beta divided by I times theta equals alpha. This term here is my omega squared term. So I know my omega is equal to the square root of beta divided by I. I should be able to go ahead and plug in those values here. Let me type those in quick for you. All right, so we get 13.6 when we get this out of there. Let me show you what we typed in though, of course. So we put in the 8.7. This was a disk, so I have 1/2 times the mass, which was 6.5 times the radius 0.12 squared, square rooted, and so my omega comes out to be 13.6 radians per second will be our angular frequency. To find the period, t is going to be 2 pi divided by that angular frequency, and our period comes out to be 0.46 seconds. And then lastly, we plug in our frequency, which is 1 over the period, and we end up with 2.17 hertz for that frequency. And then lastly, part C, they want us to write an equation for theta. Okay, so theta is always going to have that same format of A times the cosine of omega t plus phi. We're going to choose phi to be 0 here because I get to choose it wherever I want it to be when they don't tell that to me. And I know the amplitude, it's this 3.4 degrees. I am going to put that in radians though. So I have theta is going to be my 3.34 times pi divided by 180. Cosine of my omega, which I just have over here, 13.6 t. And this is all in radians with t in seconds. There you go.